final video. Let's wrap this up with things that you should memorize or know. An all-encompassing 5-minute quick and dirty version of everything about ray diagrams and lenses and mirrors. Number one, a converging lens looks like that. So if you read a problem and it says converging lens, that's what you're looking at. Diverging lens looks like that. I don't know why they use converging and diverging for lenses and concave versus convex for mirrors, but that's the separation I've seen in every source I've looked at. So converging lens looks like that, diverging lens looks like that. However you want to think about it, I don't care. Concave mirror is exactly what you think. The scoop is the cave. Convex mirror is vexing why it's called that. Mirrors will reflect light while lenses will transmit light. You should be able to draw a very rough idea. So with a converging lens, they're going to come together. With a concave mirror, they're going to bounce back together. You have to know which side of the lens or mirror the correct rays are going to be on. So for lenses, since it transmits, it's going to be on the right side. For mirrors, the real rays are going to be on the left-hand side. So let's look at both our converging lens and concave mirror, which makes sense because you could take the converging lens and whoop, tuck it right into that little nook of the concave mirror. That's because they go together. With both of these, when an object or light rays are transmitted through the converging lens, whoop, the real rays come together. The same is true for a concave mirror. When they reflect back, the rays come together. If that's the case, you're going to have a positive focal point. Anytime those real rays, and I'm going to add that real word in there, real rays come together. That's the wrong color. Real rays come together, positive focal point. If your real rays scatter, you have a negative focal point. So let's look at the two situations where your real rays will scatter. With a diverging lens, whoop, your rays will go in different direction, which means they're not going to meet together on the other side of the diverging lens. Convex mirror. When the light wave hits here, it's going to reflect up. When the light wave hits down here, it's going to reflect down. So your real rays are never going to come together. Your real rays scatter. That's a better way of describing it. Your real rays scatter, that means you have a negative focal point. So both of those situations have a negative focal point. Always be careful. Let's go through your rules first. Parallel to the principal axis and then through the focal point. Rule number 2, through the focal point and then back parallel, and then along the parallel of the principal axis. And the clause for this rule is use the left side focal point if the rays come together, and you use the right side focal point if the rays scatter, just like we drew over here. If your real rays come together, you use the leftward focal point. If your real rays scatter, you use the right side focal point. Left side, right side, right side. So it doesn't matter which of these four you're doing. Since these are coming together, you're going to use the focal point on the left. And since these scatter, you're going to use the focal point on the right. All right. At this point, after the last couple videos, you should be able to tell if an image is real or virtual based on which rays come together. Do your real rays come together and meet up? If so, you're going to have a real image. Or if you had to use the dotted lines because your real rays didn't come together and you had to draw it on the wrong side of the lens or the wrong side of the mirror, or rather, the left side of the lens or the right side of your mirrors, then you're going to have a virtual image. If the image is real, your image distance is positive, which makes sense, real positive. I keep saying correct because real images feel correct. So it's going to be positive in that situation. Rays intersect on the correct side. So on a lens, after they transmit, they intersect. For a mirror, after they reflect, they intersect. If your image is virtual, you're going to have a negative image distance. So whenever you use your thin lens equation, 1 over SI plus 1 over SO, image distance, object distance, equals 1 over your focal point. When you plug those values in, you need to make sure that your image distance is correctly positive or negative. You need to make sure your focal point is correctly positive or negative. Now notice I never discussed the object distance, whether it's positive or negative. It is, for all intents and purposes, going to be positive. The only situation I can find is, in fact, your textbook even says you're not going to have to know how to do that, but it's when you have multiple lenses and mirrors working together, which changes whether your object distance can be positive. Object distance is positive, always, because it's the object. It can't be negative, right? And rule number 3, through the center of curvature. If it's a mirror, it's going to reflect. If it's a lens, it's just going to transmit. But it has to go through the center of curvature for every material it's passing through. And one thing that I do want you to be careful about, I try not to, at some point you're going to come across a problem, and I think we did one together, where the object is between the focal point and the lens or mirror. Please be careful when drawing your ray diagrams. The rules don't change, nothing is different, but be careful with them. Just, if you need help, go back to the video where we discussed that. And despite the negatives being slightly askew on that one, everything else is good. If you have questions, let me know, and I'll do my best to help out. Thank you.